We're going to end on time, although we're starting a bit. We're going to end on time at 5:30, so whatever we don't finish in this lecture will continue at the beginning of tomorrow. There's the way that I did the lectures is there's time at the end for any kind of overflow. Okay. So we're going to start talking about the basics between absorption and setting the fundamentals for laser-induced fluorescence. So we'll give a brief discussion on the absorption process and absorption spectroscopy. Development of the laser-induced fluorescent rate and fluorescent signal equations. And that's really it, because that's kind of a challenge in itself. Okay, let's go back. So in the last lecture, we spent time examining essentially basic spectroscopy, which included a means to understand which transitions are allowed, why they're allowed, and where to tune your laser for diagnostic applications. And again, back to a graph we used there. This is an example for OH absorption. Again, if you were going to use the 0,0 band, you know that you would tune to somewhere near 306.4 nanometers. Well, here's sort of OH absorption in more detail if you zoom in, looking right around the 0,0 band, and you coming from, say, 307 to 316 nanometers. And really, this corresponds to, these are the energy diagrams, and here you can see the different vibrational levels in the ground state, the excited state, and here's where you can actually start seeing those sort of split levels, okay? And so these degenerate levels splitting, you see the splitting decreases as we go up in wave number. So the way that you can think about the entire last lecture discussed the x-axis, where, okay, you can tune to what's allowed, okay, and why, like I said in the last lecture. What we now want to look a little bit at is the y-axis in this lecture. And again, for a practitioner, we spend a lot of time on where you're allowed to tune your laser, okay? So we need to help understand in order to get these relative signals, if you will, these relative intensities of the different rotational lines at a given transition, we need to understand how the energy is distributed, okay? And so really what this comes down to is how are the individual transitions populated and what determines the relative intensities. Again, coming back, connecting the last lecture, we kind of saw the basic format of where individual stick spectra would be, okay? We know nothing about it except that we could draw a line at all these discrete locations. Now what we want to talk about is why are some higher than others and what starts to give them a finite width. So what we're going to do is develop the basic theoretical foundation behind absorption and laser-induced fluorescence first. Then, once we have that, in the context of that, we can look at the different population distributions and the different widths, okay? And that's what we have. So, because they'll be the focus of what you as a practitioner want to do. You would want to know which lines are strong, okay? Which ones are temperature sensitive, which ones are temperature insensitive. And this is all built into, quote unquote, the y-axis, okay? And so I want to point out so that you keep this in the back of your mind as we're developing these equations. Once we get to the end, it's going to be very important for you to choose the appropriate transitions if you want to use them in various situations. As I was explaining to someone at the break, which line to pick will depend ultimately on what you want to do with it. If you want a line that is temperature insensitive, then you'll pick a certain rotational line versus one that actually has a lot of temperature sensitivity. And you may be in the 0,0 band and you're absorbing too much because you have a really long path length. So we would want to back off and pick a weaker rotational line so you don't absorb so many photons. Those are going to be the type of things that you would want to think from a practical point of view once we've developed the rate equations. Okay, so an electric dipole, we worked with this a little bit on day one. Again, a dipole is just a separation of positive and negative charges, which is characterized by the dipole moment. So this is, again, the dipole moment is Q dot D, where Q is the magnitude of the charge and the D is the separation between the two charges. This is a way to just characterize. From a physical point of view, we know that there's a charge distribution in a molecule. We talked about this, whether a molecule is polar or not polar. Again, there can be non-uniform distributions of positive and negative charges. And then if that's the case, they have a dipole moment. Think of water, very polar molecule. And what we'll call these are molecular dipoles or a polar molecule. Yeah. They can have a permanent dipole when, again, two atoms in the molecule have different electronegativity. These are polar molecules, and again, they can be induced. Going back, just reinforcing what we talked about in day one. Okay, so we can already have something that has a permanent dipole, that has a different distribution of charges. Again, water is a great example. We can have one that's essentially nonpolar to start, like nitrogen or oxygen, but then it can be induced. And this will be, we'll use a lot of dipole type interactions when we develop Rayleigh scattering to kind of show how that process works. Okay, and that's actually a very neat example of how you induce a dipole moment. Okay, so let's see, if we have a dipole model, we know that the electric field, i.e. our laser for laser diagnostic, but our electric field oscillation drives the polarization in a molecule. A realistic gas, some volume of gas has a large number of dipoles, and so we have to sum up all of these, and this is given by number density. Again, and if we assume that we have an average dipole moment of Q dot D, then the summation of all the dipole moments within the unit volume is N dot Q dot D. And again, that we saw in the first lecture or the second lecture that we could write this as the dielectric constant in free space times the susceptibility times the E field. Okay, so this is again recounting what we've done. Now, a polarization is a coherent oscillation between two electronic states. That what happens is the electric field induces a oscillating dipole. So let's talk about what now when we're talking about an induced dipole. Okay, so we're polarizing the molecule, okay, through the electric field. So how do we do this? So this is kind of the explanation for it. Let's think about this. As coming back to this very simplistic model, we have this kind of large electron cloud that's surrounding the two nuclei. So when an external electric field interacts with the molecules, this electron cloud gets perturbed. Okay? Really, when we say perturbed, the electron orbits are disturbed. Okay? So the oscillation of the electron cloud results in periodic separation of charges. Okay? And so what happens is you can imagine that remember our electric field has some characteristic frequency, right? Due to its wavelength, and this generates a periodic disturbance to the electric cloud. Okay? And so we have these so what happens is these charges are being separated in this periodic nature, right? And so we're inducing a dipole moment because we're separating the charges because we've perturbed these. So at the frequency of the laser, okay, that omega, we have that frequency of disturbance and that frequency of an induced dipole moment. Okay? And so again, the dipole is also a source of EM radiation, and we'll look at this. So again, what I want you to understand here is that you have molecules that have a certain configuration, and then when the electric field comes here, it is periodically disturbing that and creating this separation, right, as it moves one thing to the other. And then as we change that separation in distance, we're actually changing that, we're inducing that moment because we're changing D. Right? And so we're having this periodic modulation of the dipole moment. Okay? So again, that's certainly the type of induced depends on the wavelength frequency of the light. We know that. And then assuming that the optical frequency of the laser overlaps in a loud transition, again, subject to selection rules, then absorption can occur. So even if we don't have an absorption, let's think about this again, and this will be the basis for scattering, at least, is that electric field comes in, disturbs the cloud, creates a a momentary dipole, so we have essentially, it's been polarized in terms of the electric field, okay? And then if we happen to be at a frequency that's allowed by the molecule in absorption line, or we're in resonance, we can actually absorb a photon, okay? So instead of just modulating and creating an induced dipole, we actually can absorb the photons. And now, that's what we're going to talk about. Now what happens is now this molecule has excess energy, and we have to do something with it. Okay? Again, so optical radiation, laser like optical electromagnetic radiation permits transition amongst electronic states. So if our wavelength corresponds to hc over delta E, if it corresponds to a vibrational energy gap, then the radiation will be absorbed, which results in a molecular vibration transition. So if our laser wavelength corresponds to a vibrational energy difference, then we get molecular vibration transition. Okay? If it corresponds to electric energy gap, that large one from one transition to the other, then radiation will be absorbed and the electron will be promoted to the highest occupied molecular orbit from the highest to the lowest unoccupied molecular orbit, okay? And so we'll show this graphically. So it really just depends on what your wavelength corresponds. If it just corresponds to a vibrational gap, then you just get kind of what a molecular vibrational transition, which is down in the IR, where your frequencies, in terms of your wavelengths, are large, but now your frequencies are small, right? And so they correspond to just a small vibrational gap. Now, if you're talking about the UV, which corresponds to very large frequencies, then these can promote an electron. Okay? So here's what we have in terms of absorption. Here's a pictorial way to describe it. We have this singular electron floating around. So we have an induced oscillation of a dipole. Okay? The rotation of the molecule turns out to be accelerated by the electric field of the incident photon to a higher frequency. So what happens is we induce it. The rotation of the molecule is accelerated by the electric field. We perturb, we move things away. It's accelerated, and we end up putting an incident photon by the incident photon, and the molecule ends up in an excited electronic state. So we've removed a photon from the incident field. We've added it to the molecule. We're now in a higher electronic state. It's rotating faster. Okay, so that's the electronically excited state. So if you look at this, we're a ground state, we absorb a photon, we go to a higher energy state. Okay, this is not a very content configuration for the molecule. Okay, so we can do some, we'll ultimately have to do something with it. Okay? So in the earliest 20th century, the first level absorption principles were introduced by Einstein. He proposed that absorption and emission of photons could be treated in a very similar manner to collisional processes. And again, collisional, we know for a long time we have the product of a rate coefficient, the concentrations, right? That's basic reaction rate kinetics, right? I have a collision, I have the larger the number I have, and a collision parameter, you know, the higher the reaction rate is, right? That's basic kinetics. But he argued that this absorption could be described by the exact same method. Okay? So what you can say then is that the overall rate at which absorption occurs can be written as W12N1. Okay? N1 is the number density of the ground state. So that's the molecules we're interested in measuring. They're all, let's say there's none right now in a higher state. So we have the number density of the ground state. And then this is just the rate of molecules between the initial state 1 and 2. Okay? So what that means is that W12, that overall rate absorption, then can be written as the integral overall new wave numbers, the Einstein B coefficient, the laser spectral irradiance line shape, and the absorption line shape. And we'll get to more of these actual shapes later on why they have shapes and what that means. So we just have an irradiance, we have a shape, okay, and we have the Einstein coefficient. Now, if the laser source is spectrally broad compared to the absorption, okay? You can work out the integral, right, if the laser source is broad, W12, the rate, right, rate of absorption can just be written as the Einstein coefficient times I nu, okay? Because what happens, the laser is so broad compared to the line shape, okay? This just integrates out to essentially 1. And so we have the laser spectral, I nu is the laser spectral radiance at the center of the absorption line. So we'll work with this right now just because this is kind of simple to deal with. So right now all you have to think is we have an irradiance of the laser and we have some Einstein coefficient, okay? So you can think about this should make sense. Let's say that the Einstein coefficient is what it is. It's a constant that describes the efficiency of the process. So the larger that is, the larger your rate of absorption would be. And the more photons you have, which is the laser radiance going up, the more absorption you get more absorption of photons you can have. Okay. Now the absorption, the Einstein B coefficient can be calculated from this expression. So let's see what this is. Again, just giving you definitions. We have 8 times, we end up having the dipole transition moment, okay? And again, if you look at this, these are wave vectors, okay? So again, that's just to give you a definition of where you can calculate it from. Now, more importantly right now is that for molecules, the Einstein B coefficient is actually a function of the electronic vibrational rotational states. We talked about this bit last time, that they change for every state. Okay, so the Einstein B coefficient can be calculated if a solution to the Schrödinger equation for the wave function has been attained. But typically that's not the case. So Einstein coefficients are determined. So you typically will measure the absorption, how many photons are absorbed, and then you go back and determine what the Einstein coefficient has to be. Now, again, one of the things that we should keep in mind are the different types of units. We have spectroscopic units and SI units. So keep these in mind as you work. Let's say as you do use the theory in your work, whether or not someone's reporting values in spectroscopic units or whether they're giving it in SI units, because there are certain conversion factors that use the speed of light. Okay, now let's talk about a little physically. As photons are absorbed, there is an attenuation of the laser beam as it propagates through absorbent medium. So obviously you want this for absorption spectroscopy. I have a detector, I send a laser in. The only way I can get my measurement is a certain number of the photons are gone, right? That's absorption. This is desired for absorption spectroscopy, but for laser-induced fluorescence, this is actually a loss mechanism, and we have to consider it in our analysis. So now the absorption of a collimated beam is proportional to the laser spectral radiance and the distance traveled dx. And then we have a proportionality. So we have the change in spectral irradiance, the path length that it's traveled, its actual irradiance, and some proportionality coefficient that's describing the efficiency of this process, which can just be called the absorption coefficient. Now you can integrate this to yield the portion of the spectral radiance that's transmitted. Okay, this is our incident spectral radiance, and this is the portion that's transmitted through the medium. So depending on the value of alpha, more or less of I nu, will transmit through. And then again, this is exactly what you expect here. As alpha increases, less of it goes through, or for a given alpha, the larger x is, the less transmits through the medium. Again, just because you'll see lots of different terminology, it's common to write the absorption coefficient as S12Y, where S12 is the line strength for a given transition. Okay? There's many different ways to write this out. Now, moving forward with absorption, or LIF, we need to consider what type of model we will use for the molecular system. So for right now, we're just going to consider a two-level model. And what we mean by a two-level model is that only only the ground state and a single electronic state, the excited electronic state, are coupled, and they're only coupled by the laser radiation. Okay? So just two levels, ground state, ground electronic state, and excited electronic state. The lower state has population N1, and the upper state has population N2. So to calculate the absorption coefficient, we need to first consider a collimated beam. It has a radiance I nu, and it has to be between frequencies nu plus delta nu, and it's going to go over a path length dx. So only a fraction of the absorbers in the lower state can absorb in this frequency range. So let me make sure I'm clear of that. You have this ground state, you have these certain number of species that are able to be absorbed, right? Or call them absorbers, molecules, whatever you want to. They're only a fraction of them only can be absorbed in this small frequency band, okay? Of the entire lower population. So we have a certain N1 in the ground state, and only a small number of them can be absorbed in this range. Now, if you go to a different frequency range, a different set can be absorbed, et cetera, et cetera. So this fraction that can be absorbed we can call del N1, and we can represent this by the interaction with the absorption line shape and the actual ground state population. Okay? Now, the reason I say that, the reason you want to think about this is when I say there's only a fraction of nu plus del nu, we're going to assume this is extremely small, but that we have some line shape that has a certain width. And so as I move my little thin, way we can think about this in a slightly different manner in case this isn't clear conceptually. Let's say I have some absorption line width, right? And if I only have some bandwidth delta nu, right? If all of my ground state that could be absorbed are distributed in spectral space, okay, then as I have some small bandwidth, I can only pick up some fraction of them. Okay? But as I move these, I pick up more and more and more. That's how you want to think about this. Okay? So that's why then this delta N is equal to N1. These are number of ground state times the line shape. Now, what we can then think is that in some volume, let's say we have length dx, we then know that there will be delta N1 dx absorbers, okay? And then they absorb at a rate W1, which 1,2 that we already identified. So the total number of absorption transitions per second is equal to the irradiance times B12 times delta N1 times the path length dx. So that's the total number of absorption transitions. So then we can write what is the total amount of energy that's absorbed over length dx. Okay? Again, we can look at this, the total amount of energy absorbed. This is our amount, this is d, the change in irradiance over this small d nu, small spectral bandwidth, has to be equal to, again, this was our rate of absorption, right? Total number of absorption transitions. Then we need to put it in terms of energy, so we have h nu c. And then we have this loss fraction, which is due to stimulated emission. And you can see it looks a lot like absorption, except now we have del N2. That's the amount that once we absorb them, they go to the excited state, and that they're given off through emission processes. So again, we're losing that. We are not keeping those in the upper state. Okay, now let's just assume that this stuff in the excited state is small. Equation 130 is actually reduced to this expression here. It's just a reduction. And then that allows us to calculate actually what the absorption coefficient is, just by comparing 131 to the previous equation. So what we now have is we have an expression for the absorption coefficient. Remember, the absorption coefficient is essentially the parameter that tells us the efficiency of the absorption process. And then we also just, through definition, we have the line strength S12. So finally, what we get to is the total fractional portion of the laser irradiance that transmits through the absorbing medium is written in this way. Okay? And which I wrote it in many different ways. We have the exponential of the optical depth. We have our line strength times the absorption shape times the path length L. We've written it in this expression, and it's also 10 to the minus A, which is also called the absorbance. These are just several different ways that you will see it in the literature when you're looking at an absorption measurement. This is the well-known Beer-Lambert law in several common forms, okay? So all you're doing is that you can see the transmission I over I naught is just equal to the efficiency of the absorption process. So TDLAS, as an example, tunable diode laser absorption spectroscopy. This is a common application of absorption spectroscopy. This is essentially, TDLAS is absorption spectroscopy with a tunable diode laser. Okay? So that means you can actually tune the laser over a spectral feature. Okay? We haven't talked about why we have a broad spectral feature. We'll get to that. But right now we're just going to assume that we have some spectral feature. And if we can tune the laser, we can tune and cover this entire spectral feature. Okay? So the way that the measurement works is that the laser is tuned over the absorption line by changing the diode current, and at each wavelength an absorption measurement is made. Typically it's done quite rapidly, scan rates as high as 10 gigahertz, and then you can average them and get a measurement even in kilohertz, multiple kilohertz, and therefore you get averaging for high signal noise ratio and high sampling rates. The biggest disadvantage of any absorption measurement, you should know since we started on just the absorption part, is that it's a line of sight path integrated, okay? So this has to always be considered when you're making an absorption measurement, okay? And so other than that, it's a very sensitive technique, okay? It can be applied with great accuracy, and you can measure lots of very pertinent species to combustion and engine processes. And here I just show an example coming from an engine where you get, no, this actually is not from an engine, but this is a very nice measurement of CO2. Okay? And from that, you can actually not only get line shape, but you ultimately can determine the actual concentration. So it's a very nice measurement. So applications of absorption measurements, and primarily TDLAS, are really in terms of laboratory experiments, flow reactors, flame shock tubes, multiple ground test facilities, engines, large-scale phenomena, pool fires, detonations, industry environments, boilers, gasifiers. You can use it in remote sensing and control, the famous scramjet flight test, et cetera, et cetera. So there's a lot of applications for just pure absorption spectroscopy. I'm not really going to go into detail. If you notice, I sort of went from just absorption principles to, hey, here's an application of it. I'm not going to deal with a lot of absorption spectroscopy because I'm more interested in looking at absorption in the context of laser-induced fluorescence. Okay. One final example is one that's in the context of turbulent combustion is within an engine. Okay? So here's nice work where there's laser, it's tuned over the water lines, okay, at 1.4 microns, motor condition, EGR characterization. You can scan really fast, but when you average, you end up getting an actual measurement acquisition rate down at 10 kilohertz, which is still great, slightly above 1 degree crank angle resolution, very good signal to noise. And you can see this extremely nice data, and then you fit it with a Voigt profile, okay? And what you can extract from this type of information is this is water concentration as a function of time. So really what TDLAS and absorption spectroscopy gives you from a very simple principle of absorbing the photons, you can actually measure the concentration of major and minor species. Now, the thing that has to, again, keep in mind is what you're measuring is a path-integrated concentration. Okay? So one has to be careful with the interpretation. All right, now we're going to take LIF, we're going to take the absorption and now move into laser-induced fluorescence background. So in the simplest form, laser-induced fluorescence is part one we've talked about. It's the absorption of laser light to an allowed optical transition, followed by a quote-unquote spontaneous emission of radiation in the form UV visible and IR light. The spontaneous isn't correct because once it absorbs, it needs some finite time to work through the energy levels before it emits a photon. Okay? But it's still fairly fast. So this is a resonant two-step process, absorption and emission. Again, this shows a concept of absorption going to various, starting from the ground state, going to various levels within the first excited state. Then this is what I showed here. At some point, there's internal conversion where it's relaxing back from whatever vibrational level that you excited to. It's redistributed and then eventually works itself down to the lowest vibrational state of the excited state. And once it's at the lowest level of the vibrational state, the molecule can return to any vibrational level in the ground state. And this energy loss, remember, so we've absorbed, you've already picked up on the fact that we absorbed a photon, so we have this excess energy, right? This molecule now is spinning around, has this energy that it did not have. And then what happens is this energy loss by going from the upper excited state back down to the ground state, or at least a lower an energy state in the in the low energy transition, in this electronic transition, has to come or can come in the form of a spontaneously emitted photon. And this is fluorescence. So again, we absorb. There's a lot of internal conversion, which is redistributing of the energy. Collisions, they make it down to the final vibrational state. And then this energy, we'll talk about all the different loss mechanisms. This thing can be hit with a collision and all the energy can be taken away. But if this energy loss goes from this upper excited state back down to the ground state, you can end up, that loss of energy can come in the form of a photon. And that's the light that we detect. Okay, that is the fluorescence. So fluorescence is not an instantaneous process because it has, you can see there's characteristic internal conversion time. Okay, so let's actually develop kind of the equations that you would use. So you go in the lab, you're going to go measure NO, you're going to go measure CO, you're going to measure OH. You're going to measure the signal. Now you want to do something with it. Okay, so let's develop the equations that you need to use to interpret your signal. So we're going to use the analysis based on the semi-classical rate equation first developed by Pipemere. So this is conceptually easier than quantum mechanical descriptions, but it does neglect certain processes. So what we're going to do is look at this type of analysis. We're going from state J to K. This may be a ground state, the excited state. This is a generic schematic. We have to think about what type of level model we're going to use. I'll talk about that in a second. What we can have is during this excitation and during this entire process, we can have quite a complex set of interaction. We can have several de-energizing processes. We'll talk about ionization, predissociation, all this before it emits photons, which gives you the signal. Okay? Now, what we need to know are all these different type of loss mechanisms to interpret, because your signal to be proportional to the ground state population, which is what you want, you have to do kind of a rate balance and take into account all these different loss mechanisms. Otherwise, your photons, number of photons you're collecting does not have a one-to-one correspondence with your actually ground state population. Okay. So we're going to start with that we assume that we have some lower energy J and an upper energy level K. These are the two that are coupled via the laser. We'll talk about whether or not you want to have other levels in a bit. But right now we just have some state J, some state K, and it's coupled. Now what we can have is that a fraction of the absorbers can be transferred to the, through the excited state through stimulated absorption. This is what we would want, right? This is our rate WI12, this is WJK, okay? So the absorb a photon, we go up to the upper state. Now the molecule can also return to its original quantum state just through stimulated emission. Comes right back down, okay? Photoionization can occur when additional molecules are absorbed and excite higher molecular states, okay? So when we have very high laser energy, so we have these very high laser radiances, we can actually get ionization, okay, assuming that their radiance is high enough, okay? And this is a loss mechanism, right? So we've sent something up to the higher energy state. If we come and ionize it, meaning we blast it apart, then that doesn't exist to come back down, right? And so this can just be characterized by some cross-section, some photoionization cross-section, I nu divided by H nu. And you can see if the I is small enough, depending on what that cross-section is, we can ignore this process because it scales exactly as the irradiance. Now, let's imagine we've absorbed a photon. Now we can absorb a second photon, right? We can have internal collisions of the atoms. We have these atoms, they can collide. Think of them as small billiard balls. And they can lead to internal energy transfer and cause the molecule to dissociate. Okay? When dissociation is produced by a change from a stable to repulsive arrangement, it's predissociation. Again, another loss mechanism. Depopulation of the upper state can also occur through inelastic collisions with other molecules. Again, they just serve as good energy sinks and sources, buffers, if you will. They can produce rotational, vibrational, and electronic energy transfer. That's what we've tried to show here. You have QKJ, QKM, and QMJ. Basically what happens is you can end up sending the energy that's you've absorbed, you have the energy in the upper state, and you can send it to all these other different vibrational levels. This is what we've talked about a little bit in the redistribution. Due to collision, you can actually transfer the energy from your upper state to all these other states. And again, if that's important, you have to keep that in consideration. Again, you have your absorption that's going up. You can stimulate and emit. You can have ionization. You can have predissociation. Okay? You can have all these different loss mechanisms in terms of rotational, vibrational electron energy transfer. The electronic energy transfer is the one that will keep most of them ion. This is quenching. We'll come back to that. And all of these vary significantly for different excited state species and if you have different collision partners. Okay? So think about what's happening. If we have here, we have something excited state, we can have rotational energy transfer is just where due to a collision, we just send it from one rotational level to another one. Vibrational energy, we send the energy from whatever vibrational level we excited to another vibrational level. And electronic and quenching, we try to send it from the upper state send it all the way back down to the ground state. Okay? And quenching, which is the one that we worry about the most, is both temperature and pressure dependent. Species dependent as well. So hopefully you're starting already to see a process that, appreciation that this process right here can be complicated. You have to kind of keep track of all these different parameters if you want to describe kind of the photophysics accurately. Fortunately, there's a lot of situations where we can neglect a lot of these, and that's what we're going to do. Okay. Again, after laser excitation, the excited state molecules can change vibrational or rotational through RT and VT directly. Again, that you don't even need a collision. They can just do it themselves. And then they can radiate, or they can actually transfer energy through collisional quenching, meaning that the molecule itself, the excited state molecule, can kind of handle this on its own. And this is internal redistribution of energy. Now, finally, you can have the original upper state, which is the laser populated state, and other nearby upper states, okay, not exact, which are populated through collisions and RET. They actually can then fluoresce, producing LIF scattered power, which is what you want. So I've talked about all these loss mechanisms, but if you keep the things up here and they don't get lost through ionization, predissociation, or these other collisional loss mechanisms, they can actually give off their light, which is what you want. And that's what we want to characterize, okay? So you have all these loss mechanisms, and then you actually have the, if you want to call it the loss from the upper state, which is what you want. So let me just make sure I understand this last bullet point. I don't think I was that clear. You can have the original upper state, which is what's laser populated. Absorption of a photon, it sends it up there, right? You actually can have the upper state, which is populated through collisions and RET and VT. So let's say other things that were sitting around here, you can actually send stuff up to the upper population through energy transfer mechanisms as well. But then finally what they can do is actually give off the light that you want, and that's the LIF scattered power, which is then proportional to the signal that you'll measure. Okay, so if we put all of this together, the excitation process is modeled by a set of time-dependent rate equations. All it does is relate the change in population of a specific quantum state I, which may be our ground state, may not be, at the rate at which collisions and radiative processes populate and depopulate state I. So right now we have it as a general state. We have any state, any quantum state I, and then we have certain things that can add to the state, and we have certain things that can take away from the state, right? So you can see already here we have a mechanism J to I, okay, which is sending stuff from state J to I. We have our absorption from any state J into I, so we're gaining here. Okay, we have other gain or population mechanisms here, but then if you see we're going from I to J, we're sending information, or we're sending population or in to other states through say quenching or some loss mechanism, some emission mechanism, predissociation and ionization. So these are your loss or depopulation mechanisms, and these are your population or gain mechanisms. Okay, so it's a balance of these different terms. Okay, so what are these terms? Basically, we can characterize anything with a Q, or rates at which collisions populate and depopulate the state. So anything here has been noted, these are where collisions, not these. But this would be a collision that's taking population from I, which is the state that we're interested in, and send it to some other state J. Now, but this is a collision that takes from any state J and sending it to I. And we have the exact same from let's see, we have W are the absorption rates. A and I are Einstein A coefficient for spontaneous absorption emission. W is the stimulated. Okay? And then we have our Q pre and Q ion, which are ionization and predissociation rates. So hopefully this kind of rate equation makes sense. This is just a balance of all the different ways that you can populate or depopulate some state I. Okay? All of this is connected because you have to know sort of what's in your state and where they're going in order to ultimately interpret the power, the fluorescence power that's coming out. Now, which model to use? What that was a very general description. So which model are we going to use? And by model, we have to say, okay, we have a certain molecular system. We have to account for absorption emission processes between the two laser-coupled states. We have to account for collisional energy transfer. Do we account for collisional excitation, photoionization, predissociation? How many levels to use? First of all, we say, do we want to account for all these different states? When do we need to account for all these different states? So this is the simplest model, and this is what we generally use. I'll go ahead and jump to that. This is a two-level model. This is just coupled between the ground state or your lowest state, and your laser in the upper excited state, coupled between just the laser. And we can see we have absorption, stimulated absorption, we have stimulated emission, we have spontaneous emission, and then we have just any collisional population and depopulation process, ionization and predissociation, okay? Now we can have a 3 or 4 level model. This now, if you notice, the 2-level model did not allow us to redistribute the energy between any rotational level or any vibrational levels. So now we can add these in these transfer mechanisms. This includes the effect of rotational energy transfer. And then we can go to 5 or 6, and we can actually now introduce the effects of vibrational energy transfer. So we have something that has no RET or VT. We can add in RET, and then we can add in RET and VT. But now once you add in RET and VT, right, that means that now for every vibrational state, you can redistribute amongst the different rotational states within any given vibrational state. So that's why you see all these different types of crossings within a state. So these models can become extremely complicated to describe the process. I tend to like the 2-level model, but there are certain times where you need to consider these other situations. We'll develop the LIF equation for a 2-level model and discuss where it's accurate and applicable. Okay? So let me introduce some of our rate equations, and that's where we'll start for today, because we'll then continue with the second half of this tomorrow. So again, this is a 2-level model. It's just the energy transfer process during a laser-induced measurement. Again, we went over this a second ago. We have spontaneous emission, A21, stimulated absorption, W12, stimulated emission, W21, and those are between the laser-coupled states. Collisional excitation, Q12, so that's collision sending stuff to the upper state. And then we have collisional transfer, which is what we usually call quenching. And then we ionization and predissociation. Okay? So if we assume that the LIF process is described only by the 2 laser-coupled states, so we don't allow any energy transfer, then we get a set of equations. Remember, we could write it generally for dNi. Well, we only have 2 states, so we write a rate equation for dN1 and dN2. Okay? And the equation should be fairly self-explanatory. If we're looking at dN2 first, this is the level where we can lose population due to ionization and predissociation. We can lose due to quenching. We can lose due to stimulated emission and spontaneous emission. And that's all based on how much is in the how much is in state 2. And we're populating state 2 we have to start with how much is originally in state 1 and the rate at which it's going from 1 to 2. Okay? So the way you can think about this, initially at time t equals 0, there's nothing in N2, so all of this is 0. So the rate of change is N1 times W12, but then we start to have some population. And if all of these are 0, then we never lose anything from the upper state, and we just keep on adding based on this rate. But now as any of these other processes happen, we will actually lose population. So it's just a rate of change equation. And we have the exact same thing for N1. We're actually losing population based on the rate of absorption, okay? And then, but we can add based on these other processes. Again, they're loss mechanisms from 2, because they're going from 2 to 1, they're gained for 1. So it's just a balance of equations right here on the different transfer mechanisms. Okay? So let's just introduce this, and this is where we'll stop for today. To solve the set of equations, some assumptions are needed. We're going to say that the collisional excitation rate, meaning that collisions populating state 2, is neglected. This is pretty low, okay? We'll still have quenching, don't worry, but we're going to say we can't populate state 2 through collisions. The upper level has a negligible population prior to excitation, so at t less than 0, N2 is equal to 0, so there's nothing initially in the excited state. That doesn't have to be true based on if it's already being excited, you know, through other processes. Let's say flame, high temperatures. You can have this. This allows an initial condition of N2 t equals 0, so it's a very nice initial condition. The total population is conserved, so we're not going to have any chemical reactions during the measurement, meaning during the actual absorption measurement and then redistribution. So during the LIF measurement, there's no chemical reactivity. So if we have no chemical reactivity, we have no predissociation and we have no ionization. Okay? If we do that, then our set of rate equations simplify quite nice. Again, the total population in N1 plus N2 at any time has to equal the amount that we started with at time 0 in the first state, right? And then we have our rate of change. The rate of change of N1 and N2 have to equal the rate of change at N1 plus N2. Okay, so this is actually a nice set of equations. I'm going to fix this typo because I don't know how you can sub 137b into 137b, but what I actually mean is that if you put in 137b into 137a, okay, you can actually end up solving this and getting this expression here, where we now have the rate of absorption, okay, the rate of absorption W12, N1, 0, and this R is all of these different loss and gain mechanisms, okay? So again, we have assumed that W12 and W21 are 0 for less than 0 and constant. So this is our first time-dependent solution for the population at state 2, okay? And it makes sense. We have our rate of absorption times the initial amount. In order to get stuff into state 2, we have to start stuff in state 1, okay? And then it's going to be balanced by all of these other parameters that are both adding 1 to 2 and taking away 2 to 1, okay? And then there's going to be a characteristic time over which this has to happen. And this is where we're going to stop for today. This is a good place to stop because what we're going to do is now start taking these LIF equations into different regimes coming here, whether we're dealing with low energy, long, short pulses, etc. Okay? So does anybody have any questions about what we did? Again, summarizing for this lecture, we started with looking at absorption phenomena, trying to describe what actually happens during the absorption process. Okay? And then we've introduced kind of the governing outline for LIF. So we'll take just a couple minutes of questions if you'd like. Ready for more networking, I presume? So, last chance, last call for questions. If not, I'll see you tomorrow. Okay.